Oh, so I should start now. Okay.
Okay.
Okay. Hello, everyone. Good morning. Welcome to my PhD defense. I've done my PhD thesis on general analysis of solar type 4 radio burst, and this is my student number, and my advisor is Dr. So, this is what I'm going to talk about in this PhD defense, which is also what I wrote in my thesis. So I will do a briefly introduction, and I will talk about the moving type 4 radio burst, and then I will talk about the stationary type 4 radio burst, and I will talk about I will make a summary and talk about the future work that might be done. Okay, introduction part. So, as you know, I'm doing solar radio burst. So, what is a solar radio burst? Solar radio burst is the intense increase of radio frequency, which means its meter wavelength, which is approximately 30 megahertz to 3 gigahertz, radiation induced by solar eruptions. So they can be classified into 5 types, like type 1 radio burst, which is here, and type 2 radio burst, which is here, type 3 here, type 4 here, and type 5. So we can actually like type 5 radio burst is a little bit ambiguous. We can actually just don't talk about it because it's just somehow a slower type 3 radio burst. So here is a cartoon of how these kind of radio bursts are generated. On the left panel is an example of a radio burst. For example, the type 2 radio bursts are here, and type 3 radio bursts are here. And for example, if the electron beam just propagates directly from the sun outward until toward the Earth, they will be type 3 radio bursts, which are pretty fast. And when they are generated at the termination at the shocks, they will be type 2 radio bursts. And if they are trapped electrons in the magnetic flare loops, they will be type 4 radio burst. And according to whether they propagate, like for example, if they are stationary, they are stationary type 4, and if they are propagating, they are moving type 4 radio burst. So here are some physical parameters of the radio burst, which are very important in the analysis of the radiation mechanisms. So first is the brightness temperature, which is the TB. And brightness temperature means we define a temperature to indicate the intensity at the frequency that equals to black body radiation. And then we have another physical parameter, which is degree of polarization. We actually define 4 Stokes parameters, I, Q, U, and V. And the general degree of polarization is like Q squared plus U squared plus V squared, the square root over I. That's the general degree of polarization. But in solar physics, we usually care about degree of circular polarization, which is only V over I. And then we have the spectral index, which is alpha. So for alpha, given a frequency F and the radiative flux X, the spectral index of alpha satisfies this equation, which means if we log left and right, we can divide log S over log F. So, radiation mechanisms for radio burst. I will briefly introduce the possible mechanisms for the solar radio burst. First, we have the gyrosynchrotron radiation, which is partly relativistic one. And gyrosynchrotron means gyration, gyro emission, and synchrotron emission. It's the combination of the two. And gyration is also cyclotron emission, which is non-relativistic, and the synchrotron emission, which is relativistic. So, and also it's also possible to be generated by only synchrotron, which is fully relativistic. So, and also like there is plasma emission, which can be further classified into fundamental plasma emission and harmonic plasma emission. And finally, we have ECM emission, which means electron cyclotron maser emission. So there are incoherent emissions and coherent emissions. For incoherent emissions, the TB is usually very low, which is no more than 10 to the 9th K, for solar emissions. So for coherent emissions, coherence means they amplify, means there is amplification, so the TB is very high. It's usually higher than the incoherent emissions. So the gyro emission. Let's first introduce the gyro emission. It's due to the acceleration experienced by electron as it gyrates in the magnetic field due to the Lorentz force. So the acceleration is perpendicular to the instantaneous velocity of the electrons. When the electron velocity is non-relativistic, which means gamma is very few. So and this is the gyration emission. So for gyrosynchrotron, as I said, it's a combination of gyration and synchrotron emission. So for non-relativistic one, it's a thermal emission, which is cyclotron or gyro resonance emission. For mildly relativistic one, it can be both thermal and non-thermal emission. So this is the gyrosynchrotron emission. For ultra-relativistic one, which means gamma is very high, it's non-thermal emission only. So this is called synchrotron emission. And the radiation frequency is equal to the gyro frequency. And for solar radio emission, the TB is usually very small, and it's usually less than 10 to the 9th K. For gyrosynchrotron emission is incoherent emission. And cyclotron emission is non-relativistic. And the polarization can be any value. It's elliptical. For synchrotron emission, it's fully relativistic. The polarization is usually linear polarized, which means there's no degree of circular polarization. And the main reason of this linear polarization is Doppler effect, which is, you can actually think about it like this. If you are here, if you observe a source, it's coming here and it's coming at the speed of light. So all other all other directions became nullified. So it become neither linearly polarized. So for gyrosynchrotron emission, it's a combination of cyclotron and synchrotron. So the degree of circular polarization can be any value. For plasma emission, first, long-mu waves are a natural mode of plasma, and they can be excited by a variety of mechanisms. I will show the cartoon of the long-mu waves too. In the solar corona, the propagation of electron beams or shocks can excite plasma waves. And these waves are converted from longitudinal oscillations to transverse oscillations. And the resulting transverse waves, they can have frequency near to fundamental or harmonics, which means like the plasma frequency or the second plasma frequency. This is the generation of long-mu waves. For example, if there's a small turbulence, like to one particle, and there will be restoring force because there are strong electric field generated by other electrons or particles, and it will come back, but it will go further from the like the equilibrium. So it will come back again. So it started to oscillate, and that's why how long-mu wave was generated. So plasma emission is therefore thought to involve fundamental emission and second harmonic emission. For harmonic plasma radiation, a secondary spectrum of long-mu wave will be generated, and the two lumbar waves can then interact to generate the harmonics. So for plasma emission, for fundamental plasma emission, it has high DCP, but usually TB is low, but not as low as you thought. It's low, but it's still coherent emission. For a second harmonic, the DCP is very low, but the TB, the brightness temperature, is usually higher. For plasma emission, it's the radiation mechanism for most type 1, 2, 3, stationary type 4, and 5 radio bursts. And fundamental plasma emission, they are usually low, the brightness temperature, but they can be amplified to around 10 to the 16th Kelvin. And for second harmonic emission, it can be 10 to the 13th Kelvin. And we also have ECM emission for solar radio burst. ECM means electron cyclotron maser, and maser is short for microwave amplification of stimulated electron, maybe electron radiation, like something like that. It's actually the counterpart of laser. Laser is what we use like pointer, and laser is light frequency, and maser is microwave frequency. So it's just an amplification of light or electromagnetic waves. And the conditions for generation of maser in solar corona is it should be like relativistic electrons, and there should be a loss cone instability. So here are the characteristics of ECM emission. ECM is usually 100% polarized, circularly polarized. It usually has very high brightness temperature, and the spectral index is they usually follow a power law spectrum. The flux frequency spectrum. And for solar radiation, ECM is usually responsible for spike burst, but there are also like type 1 or stationary type 4 radio bursts, which have been like explained by ECM emission. And this is how ECM emission is generated in solar corona. Like, for example, here are the loss cones which are needed. Like they are the hot energetic electrons which are trapped here, and here are the ion cyclotron waves, and here this is how the X-mode maser emission generates from the solar corona. So I did a study of type 4 radio burst. And what is type 4 radio burst? As I made a brief introduction of solar radio burst. And type 4 radio burst is the broadband meter wave continuum, which lasts for a relatively long time. Considering like by whether they propagate, we can classify a type 4 radio burst into moving type 4 radio burst and stationary type 4 radio burst. As you can see, moving type 4 radio burst means they actually propagate, and stationary type 4 radio burst, it's just like parallel, they barely propagate. For moving type 4 radio burst, it's usually considered to be generated by either gyrosynchrotron or plasma emission. For stationary type 4 radio burst, there is no frequency drift, but and the radiation mechanism is usually thought to be plasma radiation. And here is like a cartoon showing how the type 4 radio bursts are generated. They are either generated like in the trapped particles in magnetic flare loops, or the open field line. I mean, they are open, but they can be closed in a larger scale. So these are propagating. These are slowly escaping particles, and type 4 radio burst can also be generated here. And also, I will introduce the observational telescopes. On the left side is a solar radio spectrometer, which is a single antenna. There are many international like systems of these kind of radio spectrometers. For example, E-Callisto or RSTN. There are so many these kind of devices in the world to observe the sun. And on the right side is a solar radio heliograph, which is an antenna array. For example, you can see there are so many antennas and they form an array. It usually takes a lot of space. It's a little bit difficult to build. So currently there are only 5 working solar radio heliographs in meter wavelength. For solar radio spectrometer, it's a single antenna. For example, there are some systems, as I told you, and they can only get a radio spectrum like this. And this radio spectrum is the emission from the whole from the whole sun. And for solar radio heliograph, it's an antenna array. It's a little bit difficult to build, but instead of a single spectrum, we can actually know where the source is and how strong the source is there instead of a spectrum. Of course, they can also observe a spectrum like this, but they can also know where it is on the sun. For example, this is an image from NRH, which is a radio heliograph. So there are 5 working heliographs in metric wavelength. I'm not including the microwave wavelengths because there are some more in microwave wavelengths. There are 5 in metric wavelengths, which is actually the observational field of corona. And first, non-side radio heliograph, which is NRH, which is in France. And second, Gauri-Bidanoor radio heliograph, which is in India. And then the LOFAR, low frequency array, in Netherlands. And then the Ukrainian T-shaped radio telescope 2, UTR2. And then the Ming-An-2 spectral radio heliograph, which is Muser. And among the 5 radio heliographs, only 2 of them make their data public, which is NRH and LOFAR. And here is a comparison of NRH and LOFAR, which are the only 2 radio heliographs that make their data public. LOFAR is in the Netherlands, NRH is in France, and this is a frequency. LOFAR is a little bit lower frequency than NRH, but they do overlap in, for example, 150 to 230. And the time resolution, LOFAR is relatively new, so the time resolution is much better than NRH, for example. And here's active. NRH is from 1967 to 2015, and then they resumed observations, which I'll talk about it later. And LOFAR was built in 2012, which is very recent compared to NRH, for example. And as you can see, for frequency resolution, LOFAR can provide frequency resolution of 12.5 kHz. And NRH, they can only observe 10 separate channels of the frequencies. So the resolution is just like something like tens of megahertz, which are very bad compared to LOFAR. And LOFAR can observe IQ UV simultaneously, while NRH only observes Stokes I and Stokes V. So I will talk about the moving type 4 radio burst I studied here now. I made a case study of moving type 4 radio burst. So these are the common features of the moving type 4 radio burst. First, the polarization can be any value from minus 100% to 100%. And the TB ranges from 10 to the 6 Kelvin to very high. For example, it can be 10 to the 6 or 10 to the 13th Kelvin. And the duration of moving type 4 radio burst is usually mostly about 30 minutes. But some of them can be as long as 2 hours. And the mechanism depends on the physical parameters of the event. And the candidates of the radiation mechanisms are plasma emission, gyrosynchrotron emission, Bremsstrahlung, or ECM emission, which is electron cyclotron maser. There are some studies which claim that background type 4 is always gyrosynchrotron, but small-scale fine structures are possibly generated by coherent emission mechanisms, which means they are higher in brightness temperature. And this is the event I studied using LOFAR and this is the solar dynamic spectrum here, this image. And here is the type 4 radio burst, which I studied, as you can see. And this is a moving type 4 radio burst, obviously, because it's propagating. There is a frequency drift. And here is a type 2. Here is a type 3 radio burst, and here is a type 2 radio burst, which is a very nice event. And this event was on 2014, August 25, and it's the active region of this number. And there was a M2.0 flare, and there was actually a CME which started to appear on LASCO at this time, at approximately this time. So we actually make a more detailed comparison of LOFAR and NRH in this. As you know, I told you that I showed you this comparison of LOFAR and NRH, and we actually made another spatial resolution comparison. First, as you can see, on the left side is the LOFAR image, on the right side is NRH image in the same frequency. It's actually also 0.9, in like 150.9 megahertz, and at the same time, and at the same frequency. So we show a very nice comparison of the two instruments. And this is the beam size of LOFAR, for example, and the beam size of NRH is actually a little bit much higher. As you can see, first thing we would like to say is that the two images, the two animations, they match pretty well. I mean, okay, the blue circle is the sun, is the solar disk. First thing is that they match pretty well. So, and the second thing, in A and C, which are, for example, LOFAR observations, we see 3 separate sources, but on B and D, we only see 1 source. I mean, by saying 3 separate sources, I mean, like, for example, here, they are separate, like here. But on NRH, which is a very old instrument, well, it's still working, which is already amazing, but you can only see 1 faint source. So we can conclude that LOFAR has a much better spatial resolution than NRH. And also, we after comparing the two instruments, we dig into the type 4 radio burst. We first try to know the DCP, which is degree of circular polarization of the type 4, using LOFAR data. For now, we are going to use LOFAR data instead of NRH in this study. So as you know, DCP is V over I. And for HBA, which is like the lower 2 panels, the instrumental effect caused the V to leak into U. So we actually used the correction of the square root of V squared plus U squared over I to correct the DCP. But we actually lose the design. As we know, okay, here are the type 4 radio burst, like here are the type 4 radio burst marked, and these are just noise. Don't ignore this part. These parts are noise. So we can see that the DCP is approximately 10% to 20% throughout the type 4 radio burst, and there is a slight increase. As you can see from here, there is a gradual increase with the type 4 radio burst. And the propagation of the type 4 radio burst. We plotted the LOFAR images onto the AIA running difference images from B to F. These are the images I just described. But for A, it's actually a larger scale image, which I'll say later. So let's look from B to F first. So as you can see, the colors are the LOFAR contours, and you can see the lower frequency is it's a little bit outward, and the higher frequency, they are a little bit inward. So the type 4 radio burst, it started at around approximately like at 310 in, because we are actually using the HBA only, so it started at probably 310. And so we can actually see that the type 4 radio burst, all frequencies, they are actually propagating outward. As you can see, they're propagating outward to the right side of the sun, which means to the west, because on the sun, the right side means the west. And also, the CME erupted later. It should be generated at the expanding flare loop during the CME near the CME core, but the loop is actually not very visible in EUV wavelength. And here is the fine structures. We actually also did the fine structures. We did the zoom-in plot of 1 minute for a 12 second and 4 second. And here are the fine structures. As you can see, these A, B, C, D, it's like 1 minute, 12 second, and 4 second. These A, B, C, D correspond to these 4 squares, as I showed you in the dynamic spectrum. So we can see that there are fine structures in every place of the type 4 radio burst, in everywhere, because this is the time here is 4 seconds, and here is 12 seconds, here is 1 minute. So we can say that the fine structures are less than 1 second. And we also checked the TB, the brightness temperature, in a very small scale. For example, we chose this one to show you. We chose this one, and the blue line is how the line is going. Here is how the brightness temperature is going. So as you can see, this is a very small. It's very obvious that the brightness temperature has a spike here, which means here. So here correspond to here, the high spike of the fine structure. But also the background type 4, because we know there are fine structures, but these are the background type 4 because A, B, C, D are actually here in the background in the type 4 radio burst. So the background type 4 is also very high, like it's over 10 to the 12th Kelvin already. So we want to check the emission mechanism based on those physical parameters. So after checking the table, we make some conclusions, we make some discussions. So the gradual rise of DCP of this type 4 radio burst indicates gyrosynchrotron emission. However, the brightness temperature is very high, which is even the background type 4 is more than 10 to the 12th. It indicates a coherent emission mechanism, which is not gyrosynchrotron. Gyrosynchrotron is incoherent. So is it plasma emission or gyrosynchrotron? We note that in 1989, Melrose suggested a depolarization process for plasma emission, which is lower DCP than expected. It made it possible to explain type 2 radio burst, for example, for a solar radio burst, making plasma emission possible for type 2 radio burst. So the type 4 is most probably generated by plasma emission. However, there are smaller scale fine structures which can be generated by other coherent emissions, for example ECM, which are responsible for short time duration fine structures, which is also a spike burst. Here is a summary of this event. We did a moving type 4 radio burst on this date, and the NRH and LOFAR comparison shows that LOFAR resolves much more details than NRH, and the DCP of this event is 10 to 20%, and there is a gradual rise of the DCP during the event. And the radio source of the type 4 radio burst propagates westward, after which there is a CME eruption. And fine structures of less than 1 second are observed, and the TB of them can reach 10 to the 13th Kelvin. And even the background type 4 is 10 to the 12th Kelvin. So we conclude that the background type 4 radio burst is generated by plasma emission with depolarization process. However, it consists of smaller scale fine structures, which are different coherent mechanisms, which are ECM, electron cyclotron maser effect. So next, I'm going to talk about the stationary type 4 radio burst, which I studied. So first, let's have a look at the common features of stationary type 4 radio burst. The polarization of stationary type 4 radio burst is usually very high, which is almost 100%. And the TB, the brightness temperature, is also very high, which is usually more than 10 to the 9th Kelvin. It's usually continuous for hours instead of like moving type 4, which I talked a little bit before. It was actually shorter, like 30 minutes. And it usually gradually turns into noise storms. And the mechanism of the stationary type 4 radio burst is very similar with type 1 burst. Here is the common feature of type 1 radio burst, because stationary type 4 is very similar with type 1 radio burst. The polarization is also very high, like 100% polarized, and the TB too, and the duration is also very long. It usually contains multiple spikes, and the generation mechanism is mostly plasma emission, but ECM, electron cyclotron maser, is also possible mechanism for type 1 radio burst. I will we'll talk about the previous studies. My study here, this stationary type 4 radio burst will be conducted to get NRH and AIA combined data to locate the radio source. And we will talk about the TB, the polarization, and the particle distribution, and spectral index. We will interpret the radiation mechanism of this stationary type 4 radio burst. There are some other recent studies on stationary type 4 radio burst by Koval. He used UTR2, NRH, AIA, LASCO C2, and he focused on the coloration of the stationary type 4 with CME. He didn't analyze the emission mechanisms. So this is the radiodynamic spectrum which I studied as a stationary type 4 radio burst. As you can see, this is the dosimetric continuum, and here is a type 4 radio burst. This is the stationary type 4 radio burst. And this is the observation range of NRH, which I told you is a radioheliograph. And here are the timings. The CME appeared here, and then there is a M7.1 flare at this time, and the type 4 radio burst started here, and there is a flare continuum, which I mean here. This one started at 1 p.m. And then the flare peak at this time, and the spectrum and the flare continuum disappeared here. For now, we still can't say for sure that this is stationary type 4 radio burst, because it seems that there is a little bit drift or not. So we will confirm this later. So this is the CME eruption before the type 4 radio burst happened. As you can see here the CME. Okay, let me show you again. Okay, here is the CME eruption before that. And then this is the AIA NRH movie of this stationary type 4 radio burst. Similar with my previous study, which is the LOFAR. And I did the NRH contours of 150 to 445. I chose some of the frequencies. And as you can see, this is the time when the time, okay, 1240 is the time when the stationary type 4 radio burst started. So you can see that they are not propagating outward at all. That's why we can say for sure that the radio burst is stationary. And the second conclusion from the movie is that the sources are on an open magnetic field, which started from the foot point, and they are slowly escaping particles. They're generated by slowly escaping particles on the open magnetic field. Here is the brightness temperature of the stationary type 4 radio burst. We can read this directly from NRH file, and the highest brightness temperature is over 10 to the 11th Kelvin, which is the lowest frequency, obviously. And the higher the frequency, the lower the TB, which is obvious. And generally, in all these frequencies, the TB are all higher than 10 to the 8th Kelvin. This is the type 4 radio burst, and this is the end of type 4, because at this time the flare continuum started to appear, which interrupts the type 4 radio burst. So we will not, these parts are not very trustable. So here are the type 4 radio burst. And then the degree of circular polarization. We know that DCP, degree of circular polarization, is V over I. We can read Stokes I and V from NRH file, and we know that this is the plot we did for this event. As you can see that all of them are very high, and they are minus, which means they are left-handed polarized. So they are all from 60% to 100%. I would say that they are almost 100% polarized, which fits the feature of stationary type 4 radio burst. This is the flux frequency relation. I will remind you again, this is the time for stationary type 4 radio burst, and this is the time that stationary type 4 radio burst ends. So we actually made the plot flux frequency correlation plot from the start of type 4 until the end of the type 4, which is actually the start of like flare continuum. As you can see that the flux frequency spectrum follows a very well power law, because this is log scale, and this is also log scale, and the flux frequency. They follow very well power law distribution, and here are the alpha, which is spectral index I calculated. And here is a spectral index plot from the start of type 4 until the decimetric continuum, which we stopped, which we only care about. So we only care about this part. As you can see that the spectral index is between -3 and -4, which is a hard spectrum for this type 4 radio burst. So this is a summary for this event. We did a stationary type 4 radio burst with TB over 10 to the 8th Kelvin, and sometimes the brightness temperature can be over 10 to the 11th. And the DCP is very high, it's almost 100%, and it's left-handed polarized. And it follows a power law distribution with spectral index between -3 and -4. So we conclude that it's generated by slowly escaping energetic particles along the magnetic field line, and the source of the magnetic field line is from a loop, flare loop's foot point. And we want to know the mechanism of this stationary type 4 radio burst. We checked the tables which I concluded using previous studies, which I summarized using previous studies. And the TB, the brightness temperature, is very high, so there should be like considerable relativistic effect for relativistic electrons. And for plasma emission, alpha, which is the spectral index, is proportional to delta, which is the like particle distribution, velocity distribution function index. So for fundamental plasma emission, the TB, the brightness temperature, can't reach 10 to the 11th by power law electrons. They can be higher if the distribution of the electrons are not power law. So we conclude that this is ECM emission. This is generated by ECM emission for such low, for such high brightness temperature. And so this is the discussion of this event. Like ECM emission usually exhibit small time scale spikes, which is less than 0.1 second. However, we reiterate that long duration continuums has also been explained by ECM emission. And here is a reference. Moreover, this reference has developed a theory to explain the type 1 radio burst with ECM emission. Type 1, as you know, which is also long duration continuum. Type 1 is also long duration continuum, which is actually very similar with stationary type 4 radio burst. And then Mora-san said that close to coronal region, ECM emission might be dominant over plasma emission. Okay, here is the summary and the future work. This is the summary of the two events. First one is stationary type 4 radio burst, and second one is moving type 4 radio burst. We actually talked about it in the other way, but whatever, it's just in the opposite way. And the date of these two events. For this study, for the study of the stationary type 4 radio burst, we used RSTN, eCallisto, and NRH. For moving type 4, we used LOFAR for the dynamic spectrum. Okay, on the upper part it's the dynamic spectrum, on the lower part is the image. And then we used not only LOFAR but also NRH for the moving type 4 radio burst. And the TB of the stationary type 4 is 10 to the 8th to 10 to the 12th. For the moving type 4, we actually not only checked the background TB but also the fine structures. So the fine structures are 10 times higher than the background. The DCP of the stationary type 4 radio burst is approximately 100%. And for the moving type 4 radio burst, it's 10 to 20%. And there is a gradual increase. For the spectrum of stationary type 4, it's a power law spectrum with alpha being -3 to -4. But we didn't do it for moving type 4 radio burst. And we conclude that this is generated by ECM emission, but for the moving type 4, we say that the background is plasma emission and the fine structure is ECM emission. And I would say future works can be done on stationary type 4 radio burst. If possible, we can check higher resolution spectrum to check the fine structures of the stationary type 4 radio burst, because we didn't do that. And higher frequency decimetric continuum on the same day. This is the decimetric continuum on the same day, which is actually the same day. The event on the same day of the study of the event we studied on the stationary type 4 radio burst, but we didn't do this part. We can do it in the future too. On moving type 4 radio burst, we didn't do the DCP data for fine structures. We only did it we only did a general DCP, the change. We also didn't do the general TB data. We only did TB brightness temperature for the for the fine structures. But the data processing of the TB takes a lot of time. That's why we only did a very small part of the TB. Because if we try to do the whole dynamic spectrum, it's gonna take time. And we actually didn't do the spectral index either. We need more study to confirm the emission mechanism of the moving type 4 radio burst. Okay, thank you all, and this is the end of my PhD defense. And I will accept some questions if you have any.